Jean-Hubert, Olivier. Yes, there we go. And he's going to tell us about some molecular strategies to regulate electronic properties of π-Conjugated superstructures. So take it away.
All right, thank you. Let me just share my screen really quickly. Let's see. Can you see it in presentation mode? Yes. Can you hear me okay as well?
Yep. Everything's great.
Well, I'm glad that after 14 months, I finally get the hand of Zoom. So, so thanks again, the organizer, for having me today and for setting up this great symposium. I've learned a lot, and thanks also, Joran, for the invitation. So today I'm going to talk to you a little bit more about what we are up to in my lab at University of Miami, where we are developing new strategies to regulate the electronic properties of π-conjugated superstructures. And so our lab, it's a synthetic lab, so I guess that the pace is going to change a little bit from the other talks that we had. And essentially, I'm really going to focus on material design and characterization, and the type of tools again that we are developing in order to tweak a little bit the semiconducting properties of supramolecular assemblies, which leads me to my next slide here. So essentially, the point of this talk is going to be to introduce you to a new concept where we have shown over the last couple of years that we can tether supramolecular assembly to create electronically and structurally robust nanoscale materials. And I'm going to show you using a couple of characterization data that we can modulate to some extent both the ground state and the excited state properties of this material. I'm just going to also put my laser pointer on. So there we go. So, all right. So what you're looking at on these top slides here are fibers that are made out of interacting π-conjugated building blocks that you are seeing right there on each of the left side of each of these images over there. And so while these type of structures are great for application as for flexible electronics, for example, one of the drawbacks of supramolecular assemblies when we use them as organic semiconductors are their charge transport properties. And so that's what I'm showing you right there in red. And I don't really have to introduce what these values mean to the audience, but essentially if you compare these values to values that pioneers in the field have measured for single crystals or donor acceptor polymers, they are a couple of order of magnitudes lower than single crystals, for example. And so, of course, if we want to understand where these low values are coming from, and again, as an organic chemist, what really is of importance for us is the structure, right? And so when you start zooming in the nanoscale, of course, the intermolecular distance between each of these building blocks, right, will impact the electronic properties at the assembly level, because that's going to dictate the efficiency with which the wave function is going to overlap, right? And so, of course, that comes down to also the conformation of the building blocks into these pi stacks, as well as packing arrangement. And again, it's a very small list of reviews that I have put it right there that people in the audience from yesterday talks have worked on, and probably also a couple of folks later on in the symposium who really have done amazing work as highlighting the problems, I guess, with organic semiconducting materials. Now, again, as an organic chemist, when we start looking at these charge transport properties, what is the type of contribution that we can make? And so before jumping there, how do we build these materials that I'm showing you there on the top of this slide? Well, everything starts with a solution phase chemistry, right? So essentially you have these little red blocks there, and these can be molecules, these can be polymers, or these can be preformed assemblies, okay? So stacks of pi-conjugated building blocks that has a certain length in solution. So these are solvated nanoscale objects. And so of course, we need to translate them into the solid state, and usually what folks are doing in the community, they are using spin coating, for example, or drop casting as well. Chemical vapor deposition might also be one of them, even though it's slightly different. But at the end of the day, and you can see that I put this step in bracket, and I'm just going to explain in a second why I did that. Essentially, by using these deposition methods, then we are creating solid state samples with which we can use either to build field effect transistor, for example, or organic solar cells. And this, again, it's not an exhaustive list of devices, but just to give you a little bit of examples. Now, the reason why I put it this solid state deposition in brackets is that these are somewhat of a intermediate state that we have a hard time to manipulate, I would argue, right? So why am I saying that? Because again, right, you take this molecule and these polymers or these preformed assemblies in solution, you drop cast them and so or spin coat them. And so you're gonna have evaporation effects that's gonna kick in, right? So essentially you're gonna have local concentration effects that essentially may perturb to some extent the conformation of your building blocks while it's getting deposited on a solid state substrate. So now for me, right, I would call that it's a black box because we don't really know what's, well, I guess we know to some extent what is happening, but it's very hard to control it, right? And so that leads me to one of big statement that I'm usually making, right, is non-covalent assemblies are fragile matter composition, okay? And so what I mean by that, I mean that if I'm starting right there on this very oversimplified energy landscape profile, I can start up there with a molecularly dissolved building blocks, and I can either decrease temperature, change the solvent dielectric, or change the concentration as well of these building blocks. And eventually what's gonna happen is that I'm gonna start sampling this energy landscape. And I may reach, for example, a thermodynamic equilibrium, or if I play my card right, I can access a kinetically trapped state. The point here is that each of these states will be dictated by a specific structure, and of course, structure-defined functions, right? I guess everybody who's there on the symposium can appreciate that. And so the problem here is that if we navigate blind regarding where we land on this energy landscape, it's going to be hard to some extent to manipulate the electronic function of the materials that we are making, right? And so just to give you an example, the type of building blocks that my lab is working on is this type of pi-conjugated building blocks. Again, these are rockstar in terms of redox active chromophores, peril and diamide. I'm sure that most of you have heard about it. And so the way that we are designing our chromophore, we are flanking them with this imidazolium side chain that offers solubility in water. And so under this given set of conditions at high temperature, what we are dealing with is a fully disaggregated sample where essentially these building blocks exist as molecularly dissolved. How do we know that? We know that because we are using this spectroscopic fingerprint, 0,0 vibronic transition and 0,1 vibronic transition. And so what is interesting is that, and that's one of the main reasons why we are using these chromophores, at least to validate the tools that I'm going to introduce you in a second, is that when I'm lowering the temperature close to 0 degrees Celsius, what is happening is that you can see this inversion of the 0,0 and 0,1 transition, right? And so what that tells us that essentially what is happening here is that we go from a molecularly dissolved building blocks into aggregated species. Now, what's great about that is that we can start asking questions about degree of aggregation as a function of temperature. And so that's what this little black square here are showing you. And we can use supramolecular polymerization model that people have pioneered over the last few decades. And so essentially for these specific building blocks, amphiphilic building blocks that I'm showing you there, the aggregation mechanism is what we are calling an isodesmic supramolecular polymerization. And so what it tells us that there is essentially one elongation constant that is regulating the growth of this aggregate in solution. So remember the little red square or rectangle that I showed you in the last slide, preformed assemblies. And so again, by using this model, I won't go into too much detail, but what we can do, we can extract thermodynamic parameters, but also we can extract structural parameters such as the degree of polymerization, the number of building blocks that are stacking in average in one pi stacks, okay? So that's just to show you, right, that any change, subtle change in temperature, for example, will disrupt the optical properties of this assembly. So that's one important parameter to keep in mind. Now, of course, what we can also do, just to show you also how solvent can modulate extensively the optical properties of this small aggregate in solution. So we all have heard about good solvent and bad solvent. In that specific case, good solvent will be DMF. And so if you look at the spectrum in pink here, these are again spectroscopic signature of a fully dissolved PDI units. And of course, as I am incrementing the solution with water, essentially to go almost to 100% water, what I'm gonna have, right, is I'm gonna have this rebalancing of my 0, 0, and 0, 1 transition. So from molecularly dissolved to aggregated. And of course, we can apply a dimensionless mass balance equation to fit the degree of aggregation as a function of DMF in water. And we extract somewhat the same thermodynamic parameters that I've showed you before, as well as degree of polymerization. But again, this slide is also to show you that a subtle change of global solvent dielectric will obviously have a huge impact on the optical properties of this nanoscale object. Now, of course, there are wealth of information that one can grasp out of a really simple ground state electronic absorption spectrum. And again, we are in no means a theory group, but we are very fortunate that people have made like amazing contribution to this field. And one of them is Frank Spano at Temple University, who have developed model with which we can calculate excitonic coupling that regulates the electronic properties of the small solvated aggregates in water sample. And so essentially what Frank has told us, right, is that if you know the vibronic transition or the oscillator strengths of the 0, 0, and 0, 1 vibronic transition, you can extract the free excitonic bandwidth, which in terms allow us to calculate the excitonic coupling. And so again, right, this value by itself doesn't tell you much, but we're gonna use that a little bit later to show you that we can modulate to some extent the excitonic coupling that regulate the optical properties, both in the ground state and the excited state of this solvated nanoscale object. Now, of course, I'm talking about solid state deposition, right? What is happening now if I'm taking this sample and let's say I'm drop casting it or I'm or spin coating it, what's gonna happen is that you're gonna look at this, okay? So essentially, if I'm looking at the nanoscale level, I would almost argue using atomic force microscopy, I will see this island of amorphous materials, essentially with a high profile of 2 nanometer, and that's essentially correspond to the width of 1 repeating unit. But you do not see really hierarchical assemblies forming with this type of building blocks. Of course, we see similar features using scanning electron microscopy, where you can see these little dots forming, or at least at the length scale that we're accessing using SEM, is very hard to talk about any structures, okay? So what I'm gonna show you over the next couple of slides is really the approach that we have taken in order to develop robust nanoscale objects. And so what I mean by that, I mean that what I'm going to show you is that we take pi stacks, right, this nanoscale object, these supramolecular polymers that we are forming in water. And what we do, or the question that we started asking, is that can we make chemistry on them? So meaning that can we take these supramolecular polymers and tether them? Meaning that can we essentially lock the conformation of our supramolecular polymer in order to now access robust objects that will not suffer from temperature or solvent change, for example. So to do that, the building blocks that we have used is the following one. Again, it's a perilene diamide, nothing really special here. But now what we have done is we have these alkyne functions, right? Triple bond, which is reactive. And so essentially this type of building blocks follow exactly the same supramolecular polymerization mechanism than the one I showed you before, where essentially high temperature, it's molecularly dissolved, at low temperature, it's aggregated. We can use our model to fit this degree of polymerization. And essentially what is important is to remember that this degree of polymerization at 1 millimolar, it's around 29, okay? So now what we can do here, right, is once we have preformed our assembly at a given concentration, now I can start coming with what we are calling a molecular locker. We can call that a tether, and people in, if people in the protein communities are here, that's essentially what we are doing when we are stapling proteins, okay? And so now you have this molecular locker with 12 repeating units, between 12 to 13 repeating units, and you have this azide functionality. And essentially what is happening, right, is that we are reacting this triple bond in order to form triazole, and we are tethering the supramolecular polymer together. And so what I'm going to show you over the next couple of slides is that we are essentially accessing different material composition by doing that. So one of the appealing aspect of this methodology, I would argue, is that now that you are dealing with an object that is not purely non-covalent, you can actually start purifying them, right? Using what people have used in the protein community for decades, a gel permeation chromatography, or the polymer community as well. And so what's interesting with this methodology now is that we can start actually purifying by size the stacks that we are tethering, right? And that was not possible before that. And so, of course, we're also using FTIR just to monitor the advancement of the reaction and stop it, essentially. So I won't go into too much details here, but what I want to mention really is that now that we can use GPC to purify them, we can start asking questions about a molecular weight. And so the molecular weight of this type of entity, so that's the Gaussian I'm showing you right there, it's around 40,000 gram per mole, and that corresponds to 23 units, right, building blocks units. And that corresponds more or less to the 28 degree of polymerization that I told you before. So we are able to some extent to capture with a high degree of fidelity, I would argue, the conformation of this supramolecular polymer. So now what can we do with them, right? So now again, I showed you that before many times, so I won't go into too much detail, but the parent non-covalent assembly, high temperature, molecularly dissolved, low temperature, aggregated. Nothing really new here. But what's very interesting is that now that we have this additional covalent tether that are essentially decorating the periphery of the stacks, right? Now, at temperature at which the non-covalent assembly is fully dissociated, you can see that the spectroscopic signature in red here at high temperature is reminiscent to that of an aggregate. So what that tells us, right, that tells us that essentially even at high temperature, these PDI units are still electronically coupled, okay? So that's a good indication that this covalent tethering is working. And what we can do, we can calculate the excitonic coupling as a function of temperature. And what we see, of course, we do see a decrease as a function of temperature. Again, that tells us one thing, that tells us that as a function of temperature, there is still some structural heterogeneity happening as we are changing temperature. And that makes sense, right? Because essentially you have a solvation sphere around the ethylene oxide side chain that's going to be disrupted as a function of temperature. But the point that I want to make here is that even at high temperature, we are still maintaining a decent excitonic coupling. So even though we do have some structural heterogeneity in these samples, right? Essentially, we are still maintaining decent electronic coupling between them. So that was the first indication that this tethering systems is allowing us to develop robust nanoscale objects, I would argue. So again, right, if I'm comparing the solid state morphology of both the parent non-covalent and the log superstructure, I showed you these morphologies before, but so now that we are tethering the nanoscale object together, that's what we are looking at, right? We are seeing this elongated rod that are essentially spreading from the micrometer length scale to up to 100 micrometer. And so if I'm looking at the height profile, I have height profile of around 4 nanometer, which corresponds more or less to the diameter of, or the width, I would say, of a reacted triple bond PDI unit. So of course, we can also visualize this nanoscale, well, this rod-like structure using scanning electron microscopy. And currently we are our working hypothesis, to explain this change of solid state morphology is that not only we are rigidifying the core of the structure, but also remember that we are purifying them by size. So we are accessing a more homogeneous population of nanoscale objects that probably have a higher tendency to form these hierarchical assemblies in the solid state. Okay, so now what can we do with these materials, right? So again, these materials can be solvated in methanol, THF, water, while still maintaining their electronic structure. And so what we have done is we have done really classic cyclic voltammetry experiment, where we have taken this solution of non-covalent assemblies and locked in superstructures, and we have drop casted them onto glassy carbon electrodes. And so the question that we were interested in is can we modulate to some extent the conduction band energy of each of these assemblies? And so each of these data points that I'm showing you with my laser here are the result of different measurements. And so the first conclusion that we can make here is that you can see that the energy, right, of the, well, I guess the potential at which it takes to inject one electron into these non-covalent assemblies is spread over a wider electrochemical windows for the parent assemblies when compared to the locked-in superstructure. But more importantly is the fact that when you lock this superstructure together, you are stabilizing by more than 100 millivolts the conduction band energy of these entities. And so currently we are hypothesizing that by constraining the conformation of this nanoscale object, we are potentially engendering the formation of new electronic states that do not exist in the non-covalent assembly. So, and again, I'll be happy to answer any question that you may have on this particular slide. What I'll show you over the last 5 minutes that I have, I'll try to keep it on time for once, is the next question that we ask is that, can we use the structure of our molecular locker to tune the electronic properties of the PBI redox active core? And so essentially, we wanted to use the structure of the tether as a knob, essentially, in order to modulate the semiconducting properties of our material. And so I showed you, the data point I showed you so far was with this, what we are calling the longer locker in our lab, right? So it's a lock 13, so it's around 12 to 13 ethylene oxide repeating unit. And what we have done is we have done the same type of chemistry, but using a smaller, shorter locker that is only composed of 2 ethylene oxide repeating units. And we are using exactly the same type of chemistry to do that. Now, of course, the first thing that happens, right, is that if we probe the size of this nanoscale object using gel permeation chromatography, what we're going to realize is that we are dealing with object that has a smaller hydrodynamic radius. And in many ways that makes sense, right? Because again, the shorter tether has a lower degree of structural freedom in solution. And so again, we have probed the solid state morphologies of these materials using both SEM and IFM. And you can see that you are essentially forming this, I would argue, being crystalline material in the solid state simply by drop casting them on any type of solid state substrate. So, but I think that one appealing aspect of using a more rigid chemical lockers is what I'm going to show you now. So again, what we can do, right, is we can start asking questions about change of excitonic coupling as a function of temperature. And so again, what you are seeing in blue dots here are the excitonic coupling as a function of temperature for the lock 13, so the longer locker. And in green here are the excitonic couplings recorded as a function of temperature for the shorter locker. And it's pretty interesting to see that when we are locking the supramolecular polymer together with a shorter locker, you can see that while you do witness a small decrease of the excitonic coupling as a function of temperature, the change is nothing compared to what we have seen for the lock 13. And so that tells us one thing, that tells us that when we are dealing with a more rigid chemical lockers, essentially, we are probably to some extent enforcing a nanoscale object that is way more robust and that has limited degree of freedom when it comes to slippage, for example, of the PBI stacks. Now, what's interesting is that, and I'll I'll just go right there, is that we are also witnessing difference when we start looking at potentiometric properties in solution. So what I'm showing you there here are cyclic voltammograms that we have recorded in water or in an aqueous medium. And what I want to show you, right, is that when you start comparing, let's say, the CV of the non-covalent assembly here and the CV of the locked superstructure, there is one important difference, is that once you lock the superstructure together, you start having electrochemical signals that are reversible. So that tells us one thing, is that, of course, you have an electron transfer to the electrode that is faster, and also, since they are being monitored at the same scan rate, but also you probably have lower degree of structural reorganization that is accompanying the end doping of this material. And so that's, again, another interesting aspect of the work that we are making here, is we are hypothesizing, again, that we can limit to some extent structural reorganization upon end doping. And we are currently working more towards this direction. But to conclude, what I want to show you is a collaborative work that we are doing with Sean Roberts at UT Austin, who's an ultra-fast spectroscopist, with his graduate student, Daniele. And what we wanted to see is that if we have any change in excited state properties as a function of molecular locker. Hopefully I was able to convince you that we do witness a change in the ground state property, but what is happening in the excited state? And is there something interesting to dig into that? And the answer hopefully is yes. I'll try to convince you. So what you are looking at here are slices that they've recorded using transient absorption spectroscopy. And of course, for the unlocked assembly here, we do witness stimulated emission. You have this really diagnostic of excited state absorption. And we are picking up formation of, to some extent, PDI radical anion. But what's interesting is that once we start looking at the locked superstructures, of course, we do not witness any stimulated emission coming from molecularly dissolved entities because we are purifying this nanoscale object using gel permeation chromatography. But you can also start arguing that the ratio of charge transfer character and excited state absorption is getting changed to the extent where when we are looking at the log2 superstructure now, you can definitely see that change of ratio between an excited state that has more charge transfer character to an excited state that is more singlet in characters. And I think that the 2D maps that Sean has built here can show you this, because what you are looking at here, if you follow these black lines right there, so that's again the fingerprint of the excited state absorption. So that would be more of a Frankel type exciton. Whereas you can see that as I am migrating towards superstructure that has higher degree of structural rigidity, we are definitely picking up signals that are more reminiscent to that of a charge transfer character excited state. And so, of course, these are preliminary data, and we are currently working more on validating this model. So I guess my time is almost up. And so I'll just wrap it up. And I hope I was able to convince you that to some extent, we are able to modulate and regulate the optoelectronic properties of solvated nanoscale object, and that by using the structure of our molecular locker, we can now dial in new excited state properties. And so with that, of course, I want to thank my group, talented group of postdoc and graduate students, and of course, my collaborators, as well as the funding agencies that are keeping the light on in my lab. Again, I wanted to thank the organizer, Johan, and the chair of the session, and I'll be happy to take any question that you may have.
Well, thank you. I'll give you a round of applause since others cannot applaud for you. And you have a few questions in the chat. I think the first one came actually about midway through your talk. So it was when you were introducing the not covalently linked structures. But I'll just go ahead and ask it. So Nemo McIntosh asks if the lock structures are indeed mechanically locked to one another.
So the lock structure are, I guess they are not mechanically locked to one another, but it's really the strategy that we are adopting here is really to make chemistry on intra-stack, if I want to say that. So we are really trying to do as much as possible chemistry on one stack and not tethering stacks together in order really to have an object that we can look at.
Yeah, that's great. And then I think we have time maybe for one more question. So Hanbo Yang asks, how can you control the number of fundamental units, or do we have to achieve it kinetically first before tethering?
That's an excellent question. So we are not well, I guess we are manipulating the number of fundamental units just because the materials adopt this specific degree of polymerization, which is 28 in that specific case. But of course, one of our goals now is to validate this technology and show that, okay, so if I'm starting with, let's say, a supramolecular polymer that has 130 repeating units, can we transfer this length scale into our superstructure, right? Can we capture this number of repeating units and now have a nanoscale object that has 130 repeating units? So, and because our goal later on would be to be able to capture kinetically trapped states, as the panelist said. So excellent question.
Oh, thank you. All right, so, and you do at least have one more question there that you could probably answer in the chat during the coffee break.
Absolutely, I will.
Yeah, and in the end, but interested in giving at least 5 minutes for the coffee break. I'll thank you. I'll thank you on behalf of everyone.